And you have to think carefully what to write so you don't like use up all the space. All right. Oh, but before I forget, let me go ahead and do attendance. So today's the 29th. We've almost made it to October. Okay, LaShawn, Zoe. Let's see. Colin, Arturo, Logan. Did I miss anybody? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. First of all, we need to learn about something cool. We've actually mentioned this before a little bit, but what does it mean to say that one thing is congruent to another? So in math, they say like A is congruent to B mod M. So this M is an integer. I'm going to just assume, for just to make it easier, that it's a positive integer greater than 0. And then A and B are integers. They could be positive, negative, doesn't matter what that means. These are just any integers. What does it mean to say A is congruent to B mod M? So I'll give you an example. 4 is congruent to 8 mod 2. The reason for that is they're both even. But there's a lot of other relationships between numbers besides even. You could also say that they're multiples of 3. So can anybody give me 2 multiples of 3?
1.
Close.
3 and 9.
Yeah. 3 is congruent to 9 mod 3. So the part that says mod blank, the mod M, that's like the base which you're talking about. So that's what forms the relationship. So in mod 3 is a multiple of 3, 9 is a multiple of 3. But it also goes beyond that, though. If you add 1 to both sides, you'll get 4 is congruent to 10 mod 3. And that's true as well. So because the remainder of 4 is not divisible by 3, and the amount to which it's not divisible is a remainder of 1. 10 is also not divisible by 3, but the remainder which it's not divisible by is a remainder of 1. So those are also congruent to each other, because the amount of which they're not multiples of 3 is still the same with relation to each other. So here's where we get to the issue. How do you solve congruences in the same way or a similar way in which you solve equations? In other words, if I have the solution to a congruence like this, like x is congruent to 5 mod 7, boom. That's called the solution to the congruence, because it tells you what x is congruent to mod 7. So basically, it's not like saying x equals 5, but you can sort of think it like saying x equals 5. The solution is 5 congruent to mod 7. Okay, so, but what if I have an equation like this, though? So this brings us to our first topic. Finding inverses mod M. Finding inverse is, I'll put a plural on it, finding inverses mod M. So let's just say I had the equation 3x is congruent to 5 mod 7. Okay, now how do I solve for x? I cannot just divide by 5 and say x equals 5/3. Because the arithmetic that we're doing, actually, we're working only with integers right now. So for one thing, you get a fraction. We need to find a solution that's an integer, and it has to be congruent to something mod 7. So if you try to solve the congruence, 3x is congruent to 5 mod 7, you can't just divide by 3. In fact, in general, it's like saying, if I said, anytime I meet somebody, their birthday is always the same as mine, would that be true? Well, it could be true once or twice, maybe even twice if I get really lucky, but it's not true in general. So it's actually not even true in general that 5/3 would be congruent to x mod 7. So you might get lucky once in a while and it could turn out to be true, but it's not valid to say, it is not valid that if A is congruent to B mod M, you can, let me put this up in red above. This is not equivalent to saying that A divided by C is congruent to B divided by C mod M. So when you're working with congruences, it's invalid to divide both sides by a number. You can't, in general. Once in a while, you get lucky and it'll work just by chance. But generally speaking, you can't divide by numbers and it won't still be true because the remainder won't necessarily be the same when you calculate what the remainder is mod 7 or mod M. So how can I solve this? Well, there's actually 7 possibilities that will solve this. And what we're actually trying to find is we're trying to find the inverse of 3 mod 7. So there actually is an integer. So what are the numbers? What's the list of numbers that are up from 0 up through 6 that would have different remainders if you divided by 7? That'd be 0, 1, 2, 3, 4, 5, and 6, right? Because 7 would have a remainder of 0 divided by 7. So 7 would be the same as 0. So x is either going to equal 0, 1, 2, 3, 4, 5, or 6. It's whatever number you can multiply by that would cancel out the 3. Or actually, maybe, okay, hold on. I'm skipping ahead a step. Before I find the x, I need to multiply both sides by something because so look above, a divided by c is not necessarily congruent to b divided by c is what I said, right? But this one is true. Let me write this one in green. If a is congruent to b mod m, that does imply, so let me write this in green. Now this is a one-way implication, it doesn't go both ways. But this does imply that a times c is congruent to b times c mod m. That statement is true. So you can multiply by an integer and still get a true congruence. But you can't divide by an integer though. So how does that look? So how can we multiply both sides of this relationship 3x congruent to 5 mod 7 and get x by itself?
Multiply by 1/3.
No, we can't multiply by, we talked about that already before you got here. Because that doesn't in general represent a true relationship anymore because the remainder might change mod 7. So remember what we learned last time. Remember that we said that if AB is congruent to A mod M times B mod M, right? Remember that? AB is congruent to A mod M to B mod M mod M. So when you work with congruencies, you can replace multiple different terms by what they're congruent to. So let's go ahead and think of a number, either 0, 1, 2, 3, or 4, or 5, or 6, that when you multiply it by 3, you'd have a remainder of 1 mod m. So what's 3 times 0? So the remainder of that would be 0, right? What's 3 times 1? 3. What's the remainder of 3 when you divide by 7? 3, right? What's 3 times 2? What's the remainder of 6 when you divide by 7? 6. Okay, what's 3 times 3? What's the remainder of 9 when you divide by 7? 2, right? Okay, what's 4? We're at 4, right? What's 3 times 4? What's the remainder of 12 divided when you divide by 7? 5. Okay, what's 3 times 5? What's the remainder of 15 when you divide by 7? Close. 1. So the answer is going to be, well, not the x, but the number we need is going to be 5. So here's the secret. Whoops, here's the secret idea. Sorry, my fault. Hold on. Here is this key idea. The inverse of 3 mod 7 is equal to 5. Now that has nothing to do with the 5 on the other side. That's just a coincidence. But if I multiply both sides times 5, 5 times 3x equals 5 times 5. Now I get the congruence 15x. 15x is congruent to 25 mod 7. And we know from above that the AC is congruent to BC mod M, so that's true because I multiplied by a constant integer. So 15x is congruent to 25 mod 7. So you are allowed to multiply by integers. But according to that property that says if you have AB congruent to something, you can replace either the A or the B or both of them by what their remainder is mod 7. So what's the remainder of 15 mod 7? 1, right? We just heard that. We just learned that like a second ago. So the remainder of 15 mod 7 is 1, so that becomes 1x. And then what's the remainder of 25 when you divide by 7? 4. So the solution to x is x equals 4. Or it's not really an equality, actually, it's a congruency. X is congruent to 4 mod 7. So x could just be 4, but it also could be 4 plus 7, which is 11. Or it also could be 11 plus 7, which is 18. Just like if you want an even number, it could mean any even number. If you want a solution to a congruency, it could be any number that has that same remainder when you divide by 7. So it could be 4 or any number that has a remainder of 4 divided by 7. So the solution is x is congruent to 4 mod 7. So let's solve another couple of equations. Okay, ready? So we just learned about finding inverses mod M. So ready? So let's learn a quick theorem. So the inverse of A mod M exists if A and M are relatively prime. Relatively prime. That's not like saying they're relatively happy or they're like relatively in their prime of their life. That just means relatively prime means that they have no common divisors. So it means the greatest common divisor of them is equal to 1. There's no other number that divides into both of them except for 1. So let's try to solve a couple equations like this. Let's try 5x is congruent to, wait, did I already do that one? Okay, I forgot the equation that I just solved. Did I solve 5x is congruent to 3 mod 7 or something different? Forgot the one I did before.
It was 3x.
3x equals 5. Okay, so let's do 5x is congruent to 3 mod 7. So we need to find the inverse of 5. So it says the inverse of A mod M exists if A and M are relatively prime. So we need to find the inverse of 5 mod 7. Does the inverse of 5 mod 7 exist? Are 5 and 7 relatively prime? Are these numbers right here relatively prime? What's the GCD of 5 and 7? What's the biggest number that goes into both? 1. So since it's 1, that means it does exist. So what's the inverse? What's the inverse of 5 mod 7 equals what? So remember, there's still 7 options, 0 through 6. You can try them all one at a time. So what number multiplied by 5? So basically, we're looking for this. We're looking for a number. I'm going to call it, well, you don't want to use I for inverse, but what's another number I could use for it? I'll say Y. Looking for Y satisfying the equation 5 times Y is congruent to 1 mod 7. 5 times Y is congruent to 1 mod 7. I'm looking for what Y is. So 5 times what is congruent to 1 mod 7? Well, 5 times 0 is not congruent to 1 mod 7, right? So y does not equal 0. How about 1, 2, 3, 4, 5, and 6? Sorry, I wrote 5 twice. Oh, whoops, I skipped 4 and then I wrote 5 twice. So which one is it? So it's not gonna be 1. It's not gonna be 2. It's not gonna be 3. No, wait, is it gonna be 3? It is 3, actually. 5 times 3 is 15. It is 3. That's why it feels like it's this. Are you guys sure that this is not the same as the last example?
It's the opposite of flipped.
It's flipped. Okay, so it's not exactly okay. So, but I guess it still worked out that the y was equal to 3. Or wait, was it 5 last time? Okay, so it's 5 last time, so I guess it makes sense to be 3 this time because probably since 5 is the inverse of 3, 3 would probably be the inverse of 5. So y equals 3. So therefore, how do I solve the congruence? 5x is equal to 3 mod 7. 5x is congruent to 3 mod 7. Well, I know the inverse of 5 mod 7 is 3. So therefore, I just take that 3, and I am allowed to multiply both sides of a congruence by an integer. So multiply both sides by 3, and then you got 15x. We got 15x is congruent to 9 mod 7. But then you have to reduce to mod 7, which means find the remainder. Remember, mod means remainder after you divide by the number that you're doing the mod of. So 15 mod 7 is 1. So you go 1x. And 9 mod 7 is 2. So x is congruent to 2 mod 7. That's the solution to the problem. Perfect. Okay, so now we've learned about the first two things. Finding inverses mod 7, solving equations that are like mod something. So you've learned how to solve congruences and you've learned how to find inverses of numbers and congruences. So any questions about those two topics?
What's the mod?
But that means remainder. So like so this is the same thing that we learned before, like 5 mod 3. Okay, who can tell me what 5 mod 3 is?
2.
2. It means what's the remainder? So there's two parts to the thing. We're ignoring how many times 3 goes into 5. We're just looking at the remainder. So what is, okay, now I'll let you answer this one. What is 8 mod 3? So what's the remainder of 8 if you divide by 3?
6.
What?
2. Yeah.
2 again, you are right. Now, guess what? There's a reason why it's 2, because actually if you add 5 plus 3, you'll get 8. So anytime you add what you're modding by to the original number, you'll still have the same remainder. So like anything that's just adding 3, so every third number has the same modulo, mod 3. And every fourth number would have the same modulo, mod 4. Every fifth number would have the same modulo, mod 5. And so forth. So let me ask you one more just to make sure you understand. What is 10 mod 3? What's 10 mod 3? 1, right. Yep. Because the remainder after 3 goes into 9, the remainder is 1. The reason why mod is important for the computers is because computers always represent everything with just a certain number of bits. So everything overflows repeatedly, and that's actually used intentionally. They want it to overflow in most cases. But if something overflows without the magnitude, then that's called like a stack overflow, and then that's bad. But most computer programming is intended so that they can just keep on rolling over and rolling over and rolling over. And that's like actually what they want to happen. It saves them from like having to like compute extra stuff. So 10 mod 3 is equal to 1, and therefore that's good. Now we're going to learn how to solve systems of equations. Are you ready for that? So remember in college algebra, you learned how to solve one equation, then you learned how to solve 2 equations. So I'm at least not yet going to make you do 3, although the process is literally exactly the same. So let's solve a system of two equations. So solving systems of equations with mod. They're actually not equations. I shouldn't call them equations. Solving systems of congruences. Congruences. And then if I say solving systems of congruences, I don't even need to say with mod because that's just part of what a congruence is. So solving systems of congruences. So first of all, just like you could, the inverse of a number mod m only exists if the things are relatively prime. In general, you can only solve systems of congruences if the modulos are relatively prime. So we're going to assume that the modulo of the congruences are relatively prime. So we have to assume that first. Okay, then we're going to do an example of something like this. X is congruent to 3 mod 6, and X is congruent to 4 mod 7. How in the world do you solve a system of congruences like that? It's kind of difficult, actually, sort of deceptively difficult. So the first thing you do is we're going to call this one, we're going to find one big M, which is equal to the product of the two small m's. So I'm going to say this is like M and M, not the singer or the candy, but I'll just say that's like M1 and that's M2. M is going to be M1 times M2. So that's going to be 42. By the way, first of all, before we even start, are 6 and 7 relatively prime? Are those modulos relatively prime? Yeah, 6 and 7 have no common factors. So it's going to work. So M is 42. Now what we're going to do is we're going to calculate something. This is capital M now. M1 is equal to the whole M divided by the first M. The whole M itself divided by M1. So what's M divided by M1? So what's 42 divided by 6? 7. And M2, okay, make sure everybody's looking. Make sure you're looking, okay? Make sure you're looking. Are you looking? Okay, so M2 is going to be the M divided by M2. So what's the M? 42 divided, and what's M2? 7. And what's 42 divided by 7? 6, correct. Now, we have to find the inverses of those mod 42. So let's just look real quick. Hold on just a second. Okay, so what's the inverse of, well, it's going to be actually kind of difficult. Hold on, let me go back and see if there's a shortcut of it. Hold on. You can be distracted for a second. Just a second. I already solved this problem, but I forgot how hard it was. You had to go up to like 190 something. Let me see if there's any way of doing it. Okay, let's see. Okay, yes, there actually is an easier way of doing it. Okay, I was hoping this, I just wasn't quite sure. Okay, so actually, instead of finding the inverse of each one of those modulo the big M, we just need to find the inverse of this number right here, that number right there, modulo the little m. So what's the inverse of 7 mod M1? Not the big M1, but the little M1, which was 6. So what's the inverse of 7 mod 6? So what number times 7 would have a remainder of 1 when you divide by 6? Close. I think it would actually just be 1, wouldn't it be? Because 7 already has a remainder of 1 when you divide by 6. So make sure you understand that 7 already has a remainder of 1 when you divide by 6. So the inverse of 7 mod 6 actually equals 1, because 7 times 1 already has a remainder of 1 when you divide by 6. Now we need to calculate the inverse of the other number. What's the inverse of 6 mod? Now the other, so we need to find the inverse of this number, mod M1. And, oh, I didn't write this out, sorry. M2 is defined as M divided by little m2. Let me write that out so it's more clear. So instead of just saying what it is, I need to define what it is. So M2 is defined as little m divided by little m2, which is equal to 42 divided by 7. Okay, so we need to find the inverse of 6 mod m2, which is 7. So what's the inverse of 6 mod 7? So this is not going to be 1. You have to think a little harder than that. So what number times 6 would have a remainder of 1 when you divide by 7? What multiple of 6 would have a remainder of 1 when you divide by 7? So it's 2 times 6 is 12. 36, so it'd be 6. You're right. So 6 times 6 is 36. And that has a remainder of 1 when you divide by 7. So the answer would be 6. So here's what you do. The solution to this problem is actually kind of easy, in a way. First, let me call this number right here A1. That's called A1. And then let me call this one A2. A2. So the solution to the equation is equal to A1 times M1. Oh, by the way, let me give these numbers. There's lots of names for these letters. This is called Y1 because we're using Y's for inverses, and that's called Y2. A1, M1, Y1 plus A2, M2, Y2. And then you take the whole thing at the end, mod the little m, the m itself. And let me explain why this works. So remember, M1, Y1, M1, which is that number 7, M1 times Y1, that's the inverse of M1 mod A1. So this number right here is going to have a remainder of 1 when you divide it by that first congruence. So when you take A1, M1, Y1, and you plug it into this first equation right here, M1, Y1 modulo 6 is going to equal 1. So you're going to have 1 times A1. So therefore, X is going to be congruent to A1. So basically, X will equal A1 after you divide by 6. So when you calculate the remainder of it, you're just going to get A1. So it's going to solve this equation. Now, you might scratch your heads and say, well, what about this part, though? What about that part? Well, remember, M2 has M in it, right? And M is equal to 6 times 7, right? So since 7 divides into M2, that means that the remainder of this part is going to be 0. So when you plug this part right here, the second term, into the first equation, 6 is going to divide right into M2, and then you're going to get a remainder of 0. And then boom, you're just going to get plus 0. So you're going to get A1 times 1 plus 0 is what you're going to get. So therefore, you'll just get A1. So X will automatically equal A1 when you plug it in the first equation. When you plug the X value right here into the second equation, you're going to be doing modulo 7, right? Well, notice M1 has M1 is 42 divided by 6, which equals 7, which has a 7 in it, right? So when you take this term right here and you do modulo 7, then you're going to get 0. The 7 divides into 7 with a remainder of 0, right? So this term is going to be 0. And then when you plug this, so it's going to be 0 plus this. And when you plug this term right here into the second equation for X, you're going to have M2, Y2. And remember, M2 times Y2, M2 times Y2. Y2 is defined to be the inverse of 6 mod 7. Then we take M2, which is 6, times Y2, we're going to get a remainder of 1, because these two are inverses of each other mod 7. We're just going to get 1 times A2. So when you add this X value right here into the second equation for X, it's just going to come out to be nothing but A2, right? So A2 is just whatever number that is on the other side. So we're going to get x equals a2 in the second equation, we're going to get x equals a1 in the first equation. So that's the reason why it works. So let's calculate what this is. So x is going to equal a1, which is 3, m1, which is 7, times y1, which is 1, plus a2, which is 4, plus m2, which is 6, times y2, which is 6. And this is all mod m, and m is 42. So mod 42. So what's 3 times 7 times 1? 21. So it equals 21 plus, what's 4 times 6 times 6? It's going to be a big one, wow. 144. Okay, and what's 21 plus 144? 165. Okay, now we need to, now the final step. Now 165 is a solution, except they want the solution to be mod 42 though. So the solution they want is actually 165 mod 42. So what's 165 mod 42? So if you divide 165 by 42 and you get rid of the answer and you just calculate the remainder of it, what would that be? By the way, there unfortunately I don't think there is a mod key on your phone calculator. 39. Yeah, that's what I get. So x equals, now really, I like to say x equals 39 because it's true that that's the first answer, but that's really not all the answers. So you should say x is congruent to 39 mod 42. So there's not really just one answer, but that's the key answer though. So the solution is any x value that's congruent to 39 mod 42 is the answer. Perfect, good job. And now this would work with more than 3, except the only thing is arithmetic would get slightly bigger. So it's not like the equation, like the equations in algebra where it gets exponentially harder each time. Instead of having 2 equations like this, you'd have m1, m2, and then m3. And m3 would be m divided by m3. And then you, instead of having 2 terms, this one plus this one, you'd have 3. You'd have a1, you'd have a2, and then you'd have a3. Then you'd have to calculate all 3 of them added together. So in fact, but let's not take it for granted though. Let's check and see if this really works. Let's test it out. Plug in 39 to this equation. What if you take 39 mod 6? What is 39 mod 6? 3, correct. So it works in the first one. And what is 39 congruent to mod 7? 4, yeah. The 7 goes into 35, and the remainder of 39 compared to 35 would be 4. Yep. So it worked. By the way, this is called the Chinese remainder theorem. They figured that out. So the last thing we're going to learn about today is called Fermat's little theorem. Okay, yeah. So by the way, Fermat has like a bigger theorem, and then also there's something called Fermat's last theorem. You ever heard of that? That's the one that Andrew Wiles proved in like the 1990s, and it took him like 5 years, like working all day long and all night long, maybe not quite, but close to figure that. What?
Plus.
Is that the what? Yeah, right, exactly. And the thing was, he said that he had a beautiful proof, but it was a little bit too big to fit in the margin of his notebook. And so people always wonder if he really did actually have a smaller proof for it, but they're not sure. Because nobody's been able to think of a small proof for Fermat's last theorem, but this is not his last one, this is just his little one. Fermat, now I'm going to change the way of it. Now, once again, unfortunately, this book, since it's written by computer scientists, sometimes the way that they write things in math is a little ambiguous, but I'll write it the way that the book writes it, and then I'll explain why it's kind of ambiguous. Fermat's little theorem. Okay, so assume P is a prime. Now you know what a prime number is, right? That's the number that only one in itself are divisible into, right? So assume P is a prime number, and assume that P does not divide into the number A. If those two statements are true, if P is a prime and if P does not divide into the number A, then this congruency is true. A to the power of P minus 1 is congruent to 1 mod P. That's pretty strange. And then the book just says and or moreover or something like that. Look, yeah, it says furthermore, it says furthermore, A comma A to the power of P is congruent to A mod P. And when I had number theory in college, I'm pretty sure that the second statement actually didn't require the second condition. So I think actually the theorem should start like this, and it should say, assume P is a prime, then you know that A to the P is congruent to A mod P, period. And then it should say, and if you also assume that P does not divide into A, then A to the P minus 1 is congruent to 1 mod P. So I think you only need both conditions to prove the first statement is true. I think you only need to assume that P is a prime for the second statement to be true. But I'll have to check into that a little bit more. So let's just go ahead and just figure out what this means. So somebody give me a prime number, maybe like anything lower than 20. 7? Okay. So let's just do the example P equals 7. Okay, good job. And now give me a number that 7 does not divide into. Yeah, you're making it too easy though. Okay, that's maybe too hard. Okay, give me a number like between 10 and 20 that 7 does not divide into. Okay, 19. So let's say A equals 19. Okay, so whoa, this is actually gonna be kind of big. That's okay though. So A is equal to 19. So first, which one do you want to check first? A to the power P is congruent to A mod P, or do you want to check that A to the P minus 1 is congruent to 1 mod P?
Start
Start at the top. So let's check to see if A to the P minus 1 is congruent to 1 mod P. And we'll have to use that property repeatedly that says that if you have A times B, you can reduce A and B both mod M. So, ready? So, plug in A is 19. So, 19 to the power of 7 minus 1 is supposed, now this is a question mark, we don't know if it's true or not. Is it really congruent to 1 mod P? Mod, what's P again? 7, right? So, first of all, what's 7 minus 1? 6. So 19, so this is basically saying that 19 to the power of 6 is congruent to 1, but we don't know for sure, so I'm going to keep putting a question mark there. Mod 7. So let's remember how to solve modular things. I mean, not how to solve them, how to reduce them. What you can do to reduce them is write out the 19 times 19 times 19 6 times, like that. 1, 2, 3, 4, 5, 6. And remember, in congruences, you're allowed to replace any factor or any term by what it's congruent to modulo whatever you're dividing by. So basically so this basically means we're dividing by 7 and calculating the remainders. And it's legal to go ahead and divide each of these factors by 7 and replace them with their remainders. So what's the remainder of 19 when you divide by 7? 5, because 7 goes into 14 and leaves you with 5, right? So we're going to replace this with 5 and this with 5, and this with 5 and this with 5, and that with 5 and that with 5. So the remainder of 5, 5, 5, 5, 5, 5 is the same as the remainder of 19, 19, 19, 19, 19, 19. By the way, do you think that we're going to have so much time that goes by that we'll get to the year 19, 19, 19, 19, 19, 19? What year would that be? That would be like more than, wait, 1, 2, 3, 4, 5, 6. That'd be more than like a million times a million years. I'm not so sure if we'll get that far. So what if they actually find like a way of like living forever? And then what if like one of us is actually alive in the year 1990? Well, let's go to heaven, you won't be. So, okay, so there's that. Now what can we do? Is there any, are we stuck? Can we go any further? Because you can't replace, well, you could replace 5 with what is congruent to mod 7, but the remainder of 5 divided by 7 is still 5. So what can I do next? Well, let's combine the 5 times 5 together. So 5 times 5 is 25, right? So that's 25 times 25. Hold on, I need some more space. So I'm going to erase the title from Oswald theorem. And I'll use that. So we've reduced the problem to be 25 times 25 times 25 mod 7. 25 times 25 times 25 is congruent to question mark 1 mod 7. Right? So can I replace anything now by anything smaller? Yes, because remember, if you have a times b times c, you can replace any factor by what is congruent to mod 7. So what is 25 congruent to mod 7? 4, correct. So I can replace that with 4, 4, and 4. That reminds me of the 4, 4, 4 at Winnie's, which they don't even have a 4, 4, 4 anymore, so tragic. So inflation. So what is 4 times 4 times 4 congruent to mod 7? Well, 4 times 4 is 16. So I can replace that with the 16 times 4. Now, what is 16 times 4 congruent to mod 7? So is this making sense? We're just finding the remainders of things. What is the remainder of 16 when you divide by 7? It'd be 2, right? So I can replace the 16 with a 2. So I get 2 times 4 is congruent to what? Mod 7. Okay, well, 2 times 4 is 8. What is the remainder of 8 when you divide by 7? 1. So it is true. So it actually worked out to be true. But that's just one example of how that it's true. So it did work out to be true for that particular combination of numbers like that. Okay, perfect. Anything else? Can you think of any questions that you might have about this? Okay, well then let me try to answer the question, why would you want to do this? Well, remember that we previously learned the binary it's called a binary modulo arithmetic expansion theorem or something like that, where you basically, if you wanted to find the value of something to a power of, let's say, remember, hold on, let me go back to this. Remember, if you wanted to solve something like 3 to the power of 71 is congruent to what mod is like congruent to what mod 5, for example. How did we learn how to do that? We learned that you took the power of 71 and you expressed that as a base 2 number, right? Remember? Or am I just dreaming? We talked about this, didn't we? We learned about base 2 and everything like that. And then why would it help if you had expressed 3 as, yeah, we did. I remember. I do remember talking about this. Why would it help if you expressed 71 as a base 2 number instead of as a base 10 number? Any questions? I mean, any ideas? Because if you express 71 as a base 2 number, then it's actually written as different powers of 2. It's like 3 to the power of 2, to the power of 2, to the power of 2, and so forth like that. Remember we talked about that one time? We had like something with several different powers of 2 on it. And every time you express it as a power of 2, you just simply square the number you had before and then calculate one more remainder. So it makes it easy. But instead of doing the binary expansion theorem, now that we know Fermat's little theorem, we can just simply replace the power of, so how can we apply Fermat's last theorem to this? So what's the value of A? A equals 3. And what's the value of P? P equals 5. And what's the value of N? N minus 1 is the same, sorry, yeah, P, okay, sorry, P minus 1. So if we use A equals 3 and P equals 5, then we know that A to the power of P minus 1 is congruent to 1 mod P, right? How can I use that theorem to reduce this exponentiation problem? 3 to the power of 71 is congruent to what, mod 5? How can I reduce this using Fermat's last theorem instead of doing it the binary theorem? Well, let's plug in the numbers 3. So 3 to the power of 4 is congruent to 1 mod p, right? So that's what it says. Fermat's little theorem says that 3 to the power of 4 is congruent to 1 mod p. How does that help us solve 3 to the power of 71? You might be saying, well, 3 to the 4th is not the same as 71. Well, instead of expressing 71 in base 2, here's something a lot easier. Express it not in base 4, but express it as a multiple of 4. So express 3 to 71 is equal to 3 to the power of 4 times something plus 71 mod 4. So what's 71? So how many times does 4 go into 71? How many times does 4 actually go into 71? It goes into 60 15 times, right? 15, 16, 17, you're right. And what is 4 times 17? 68. And so what's left? 3. And so since 3 to the 71 is equal to 3 to the 4 times 17 plus 3, I can write that like this. 3 to the 4th power to the 17th power times 3 to the 3rd power, right? Because I can just simply factor out the 17 from the 4 and write as 3 to the 4th to the 17th power. And then anytime you have 3 to the a plus b, you can factor out 3 to the b just on the side. So the congruency problem, 3 to the 71th, can be expressed as 3 to the power of 4 to the 17th times 3 to the power of 3 is congruent to what? Mod 5. See how that changed? Now, what is 3 to the power of 4 congruent to mod 5? By the way, I forgot to plug in the p equals 5. So imagine imagine I really plugged in 5 for that p. So what is 3 to the 4th congruent to mod 5? According to Fermat's little theorem? 3 to the 4th is congruent to 1 mod 5. And we already know from the theory of congruences that you can replace any factor in an expression that's in a congruence by what that factor is congruent to. So since 3 to the 4th is congruent to 1 mod 5, that means I can replace 3 to the 4th by 1. So I'll go 1 to the 17th times 3 to the 3rd is congruent to what? Mod 5. So what is 1 to the 17th? It's just 1. So this whole term just drops out. I just now have to find what is 3 to the 3rd congruent to mod 5. So does anybody know what 3 to the 3rd is congruent to mod 5? 2, because first of all, what is 3 to the 3rd? 27. And 27 has a remainder of 2 after you divide by 5. Yep, so the solution is 2. See that? So that's actually a lot quicker than the binary expansion theorem that we learned. Because instead of expressing an invariant in binary, all you have to do is just find one prime number like 5, and then p minus 1, which would be 4, is congruent to 1. So then you express the previous power as a multiple of 4 times whatever plus 3. Basically, in fact, this part doesn't even matter because that part's going to be 1. This is the only part that matters. So basically just you take the remainder, 3 to the 3rd, calculate what that is mod 5, and then you're done. Any questions? Okay, that's a good stopping point. There's no homework for today, but however, though, I do want you to look at the problems that are in section. This is all in section 4.4, the one right after the one we did last time. So look at all the problems and things, read through carefully in section 4.4. And also let me check attendance one more time, just for the ones of you that might have gotten here a little bit late.